Okay, thank you very much, Boyan. So I will try to go very quickly through a brief presentation of TEKNIKER's activities first, and then I will focus on the MOSAIC project. So for those that do not know us, we are a non-profit private research organization. We have been in the research field for nearly 40 years. And if we want to summarize our activities, maybe manufacturing is the main field or activity for us, considering manufacturing as not only manufacturing processes, but designing equipment and means for manufacturing. We are around 300 people. Our budget is in the range of 25 millions. Most of our incomes come from the private sector with direct contracts with the companies, but we are also very active at European level. In fact, we have more than 30 years of experience in European projects with more than 250 projects along this history, and a good part of them have been led by ourselves. If we try to summarize TEKNIKER's activities, maybe we can group them in four main research areas. One will be advanced manufacturing, other will be related with product engineering. We are also very active in the surface engineering field, developing coatings and means to implement those coatings, and also ICT is one field. If trying to focus on renewable field, we work mainly on concentrated solar power, on CSP, photovoltaics, wind energy. We also work on energy storage, not only thermal energy storage focus on CSP, but also we have developed for redox flow batteries and hydrogen, and also we work on efficiency and electromobility. This is more or less 25% of our incomes in general. I will now focus on CSP. For CSP, we normally work developing components and systems. On one hand, we develop coatings for receivers and for mirrors. In fact, inside InPower project, our main activity is related with selective coatings for linear receivers. In fact, we can produce these coatings in 4 meters long tubes. So we can produce, let's say, real receivers for application. We also work in new concept of concentrators, new heliostats, new tracking systems, and also new CSP power plants concept, like the one developing in MOSAIC project that I will present later. And we also develop procedures and means for coatings, and also systems to verify assembly process, geometry accuracy based on autocollimators or photogrammetry or other techniques. Regarding the heat transfer fluids and the thermal storage media, we also develop new molten salts or additives for them. We also work on the development and characterization and monitoring of heat transfer fluids. And of course, we also model, simulate, or design thermohydraulic systems. And we have also different test benches to test the degradation of the molten salts, but also to test the compatibility of any components of the system in real conditions up to some temperatures. Finally, we also work deep in operational maintenance of the plants. We can maybe group many of our developments under what we call smart CSPs, that is to trying to apply Industry 4.0 approach to the CSP, developing ad hoc sensors to measure reflectivity, dust, tilt, HTF degradation, and other parameters. to analyzing all these data with big data techniques, developing new controls, and so on. We have also been developing automatic calibration systems for heliostats. In fact, this development has been in cooperation with FENER and will be presented later inside the Capture project. We are always working in the reduction of water consumption for the cleaning systems. Many of this work has been also developed inside WASCOP and Sorwaris projects and will be later presented probably by TSK. And we also work in other validation process and verification process in the field for the heat transfer fluids, for the collectors, and so on. We have been working with many of you, and we are participating in all relevant associations, and we are participating in many European projects. Today, 3 of them are being presented, and I will focus on the MOSAIC project right now. So, regarding the MOSAIC project, first I will try to explain which is the motivation. First, I would like to thank the European Commission for the support of this project, and of course, what I am going to present is not only the work of TEKNIKER, but a strong consortium with 10 partners involved in it. As for most of the projects, the final goal of MOSAIC is trying to reduce the LCOE of the CSP technology. And we are focusing on different points. On one hand, what is clear is that the solar field is the most costly part of the plant. So we must focus on it, and especially on the tracking system that are one of the most expensive parts of the system. But we cannot forget that if we want to reach high efficiencies, we need high temperatures. So we need 3D concentration to get these values. And on the other hand, we are proposing a modular system in order to achieve high efficiencies, but with a lower cost. So in order to reach this goal, our approach is to use fixed solar fields that have a great potential for cost reduction. So using spherical concentrators that have been used, but not very often in the past. In fact, if we see all relevant scale prototypes were developed in the last century. Here are the most relevant ones. So, which is our approach? Our approach is to use spherical reflectors because they can be fixed because for any incident angle of the sun, a spherical reflector reflects the sunlight into a line. So we can use a linear receiver with a 3D concentration, and we will need only a single tracking system that moves the receiver to track the concentrated flux. But when we go for large systems, this approach implies very big civil works. So what we are doing is to consider that different spheres with the same center point will still concentrate the light in the same line. So we can use different spheres providing that the center of these spheres is the same. So we are proposing a semi-Fresnel approach for these spherical concentrators. And on the other hand, we will use a number of modules so that we can get very large solar plants, so very effective power blocks, but with low attenuation losses, so very good optical efficiencies. So the approach is summarizing a multi-ball plant concept based on spherical semi-Fresnel concentrators with an novel tracking system that I will explain later. So the intended benefits for this approach are to keep the cost down, especially because the solar field is fixed, no wiring is required, no tracking system is required. We will have quite high concentration ratios with 3D concentration in a line. This concentration is progressive from the bottom, from the mirrors to the top. So we can get high temperatures, high efficiencies, and effective storage systems. And finally, we will have a modular approach that will allow us to validate the whole system with an affordable investment. The system will be suitable not only for large plants, but also for distributed applications. If we go for large plants, the power block will be very cost effective, but the attenuation will be low and the pointing accuracy requirements will be low. Finally, we can share different elements like the towers or the module storage systems between different modules. Of course, not all are good news. We have some challenges to solve. On one hand, we will have quite tough flux conditions because we cannot defocus the solar field. The solar field is fixed, so the concentrated flux will be there above the solar field at any time. And on the other hand, when we go for very large spherical concentrators, the classical tripod systems to support the receiver become very, very expensive. So we are proposing a different approach for the tracking system. Okay, so let's go for the development of the system. What we are proposing is a plant composed of a number of modules, and each module will look like this. We will have a tracking system based on 8 cables supported on 4 towers around the solar field. The solar field will be composed of a central spherical ball and a number of rings belonging to different spheres, but all with the same center. We will have a linear receiver and a flexible tube that join this receiver with the fixed thermal loop. So if we compare our approach, that will be the one on the right, with the actual sphere approach that was used previously, we see that we can reduce the shadowing and blocking compared with the actual sphere, and also compared with a pure Fresnel approach. We can reduce greatly the civil works, so the expenses of the solar field, and we will have tried to get an optimum solution for this approach. If we look at the receiver, this is the cylindrical receiver, and this is the accumulated flux along the year. We see that if we unwrap the cylinder, we can see here this flux distribution. We see a number of peaks that correspond with the different spheres that we are using. This corresponds with a central ball and 3 rings around it. This solar flux is not uniform, as we have seen, but it is not constant along the year and along the day. This corresponds with the situation on March 21st at 8 o'clock in the morning, 10 o'clock and midday. So the flux is quite uneven and quite variable along the day. And of course, we can imagine that for different hours along the day, the contribution of the solar field, that is what we are seeing down, is very different. At early in the morning, the west part of the solar field is reflecting the light on the receiver, and at the midday, most of the solar field is working. But the contribution of each part of the solar field is not the same. So if we see the energy provided along the year by the solar field, we see that there are many parts that do not contribute very much to the energy. So there are a number of, some parts of the solar field that could be removed with nearly no loss in the energy, but a great cost reduction. And we also can get some corridors to access the mirrors. That is also very interesting for the application. So when we go for the real implementation of this system, we see that implementing these rings, continuous rings, is not the best approach, the most cost-effective approach, but we are proposing to use two kinds of modules. In the central bowl, we will use modules with 25 mirrors, 1 square meter per mirror, so 25 square meters per module. And around these modules, we will have modules with 9 mirrors, 3 by 3 modules, so 9 square meters. In this way, we can standardize the manufacturing process and get a more cost-effective approach. Regarding the tracking system that I have started to talk before, what we're proposing is a parallel kinematic approach based on cables. In this way, the tracking system can be very cheap, so there is a potential for cost reduction. We have checked that we can reach all the workspace, all the positions that the receiver must reach. And on the other hand, we can share the structures, the towers between the modules, so we can reduce the cost also. So the real view of this tracking system will be something like this, with 8 supporting cables, 1 crosshead at the top of the receiver and 1 straight beam at the bottom that will support the receiver during the movement. One critical point here is that we are using a quite flexible tracking system and a quite complex, because it's a hyperstatic system. So a quite complex control system is required. Due to the flexibility of the system, we need a closed loop control system. We cannot use an open loop system. So we have incorporated a non-contact optical control system based on fixed cameras that are attached to the towers, and some lights on the towers and some near lights on the crossbars on the beams that are supporting the receiver. So these cameras in the tower systems will be looking at the receiver and looking at the lights that are at the towers, and after some image processing, we will be able to identify the receiver position, and we will use these targets on the towers for self-calibrating the whole system. So where are we now? We have built up part of the system already. We have on the field the tracking tower systems. We have the skid, the thermal loop already in place. We have the foundations for the solar field. You can see it here on the floor. We are starting to manufacture the modules. Here you can see a 3 by 3 module with 9 square meters. We have produced already, Rio Glass have already produced all the mirrors. They are curved mirrors, spherical mirrors, curved to the right curvature for each ring. We have checked the accuracy of the mirrors that have been good for the application. And we are also developing the alignment checking process for the modules. Thanks to the characteristics of the spherical concentrators, If we use a laser beam located at the center of the sphere, at the right distance from this module, the light should be reflected directly to the same point. So it is quite easy to check if the counting process is right or not, and to modify the system. Regarding the receiver, it is a linear receiver, except for the top part of the receiver that is a conical shape. It is composed of three different coils, and the heat transfer fluid will enter by at the bottom, and we go up to the top of the system. Here you can see some photos of the system with part of the isolation already installed. And here we can see the thermal loop that has been built up by Albor in a skid. This skid is now installed at the top of a fifth tower that give access to the center of the spheres that will be here. And we have also incorporated a parking position where the receiver can be put during the night or for maintaining operations. Finally, the tracking system is now being installed and verified. The drums are on site, the pulleys, the active towers to check the positions have been checked. We are now solving some props issues that have been have appeared, but all the system is ready for the first verification for the setup of the tracking system. For this operation, we will not use the real receiver for security reasons, but we have built up a dummy with the same geometry, with the same size. And we have already installed the crossbars with the lights on them, and we have started to verify the system. Here you can see the first test where we can see the image that one of the cameras in a tower sees, and how after processing we can identify very clearly the targets for verifying the system. So as a conclusion, we have proposed a new CSP concept with good cost reduction potential. The components have been already designed and manufactured. The assembly process is ongoing, so the system is under construction, and in the coming months we will test it so that we can validate the system and identify which are the most promising commercial application of the system, not only for large plants or distributed plants for electric production, but we are also considering the application of the system for the production of solar heat for industrial processes. You can get much more detailed information on the articles that we have already published, and on the website, and there are some animations on YouTube also. And I think that's all from my side. If you have any question.